In this lesson, we're going to talk about how to use the chi-square distribution for hypothesis test. There are 3 different tests that we'll be looking at in our class that require chi-square distribution: the goodness of fit, independence, and homogeneity of proportions. The goodness of fit is actually our first hypothesis test on categorical data. If you remember back from chapter 1, when we talked about the different types of data, we had quantitative numerical data or qualitative categorical data. Quantitative was all about numbers, and that's what we've been working with so far with our hypothesis tests. But here, for a goodness of fit test, we can actually use this test on categorical or nominal data. When we perform a goodness of fit test, we're looking if the frequency distribution fits a specific pattern. So do we have a uniform distribution where all of the values are the same, like flipping a fair coin, or maybe the same number of something on every single day? Or is there some established pattern that we want to match it to? So one example is the distribution of colors for M&Ms or Skittles. Skittles is actually uniform, so that one isn't as much fun as working with the M&Ms, as the M&M colors are not uniform. Another example of goodness of fit that's following an established pattern is something called Benford's law. Benford's law is a very fascinating distribution of leading digits in data. And so there's an example a little bit later where we'll be looking at Benford's law in a little more detail. Independence of 2 variables. This is talking about the independence for probability. So all the way back from chapter 4. If 2 events are independent, then the probability of A and B is equal to the probability of A times the probability of B. And so we can test whether sample data indicate 2 variables are independent. Are the number of infections independent in a hospital? Organ transplantation and the years in which they are performed. Crimes compared to location. So this is an example of independence of 2 variables. And then homogeneity of proportions. Do I have 2 populations with the same proportions of subjects with certain characteristics? This is different from our hypothesis test on 2 proportions because we're not just looking at 2 proportions for 2 populations. We're actually looking at multiple proportions across a spectrum. So it makes it a little bit different. And 2 definitions for us. We have something called observed frequencies, and this is just our data. What are the frequencies obtained from the data? Usually we denote this by the letter O. And then expected frequencies. Frequencies obtained through a calculation. If we fit a certain distribution, these would be the frequencies that we expect from that distribution. And we denote expected frequencies by E. And a goodness of fit test is a hypothesis test to determine whether a single row or column of frequency counts agrees with some specific distribution, such as uniform or normal or something else. We have some notation. K is going to represent the number of different categories or cells. N represents the number of trials or the total number of observed sample values. And P is the probability a sample value falls within a particular category. And some requirements: the data have been randomly selected. Notice that comes up every single time. It's so important. Sample data consist of frequency counts for each of the different categories. And for each category, the expected frequency is at least 5. And notice this is expected, not observed. So the expected frequency is at least 5. Expected frequency for a category is the frequency that would occur if the data actually have the distribution that's being claimed. If we have a situation where one of the categories is not expected to be 5, we could group that category with one of the other categories if it makes sense in order to use this distribution. We can do some work so that we can apply this distribution if we want to test something out. The hypotheses for our hypothesis test: the null means our frequency counts agree with some claimed distribution, and the alternative, they don't agree. And this is very similar to it's equal or it's not equal. So that's one way to remember it. The test statistic formula given here, but we're not going to do this by hand. Excel and Google can do this for us. So we're going to let Excel and Google take on this. Goodness of fit hypothesis tests are always right-tailed. So even though we have an equal to and not equal to, when we're doing our chi-squared test, we'll always be looking at the right tail on this distribution. And then the last thing to point out, our degrees of freedom for this goodness of fit test are k minus 1. And remember, k is the number of categories or cells that we have. So degrees of freedom is not n minus 1 like it was for the t distribution. And that's what makes this a little bit different. And then the last thing before we can do an example, conducting a goodness of fit test requires that we identify observed frequencies denoted by O, and then find the expected frequencies with the claimed distribution. And there are two different approaches for finding those expected frequencies if we're looking at a uniform distribution, where the expected frequencies are all equal, then all of the e's in our expected frequencies will be n divided by k. So n is the total number of observations that we have, and k is the number of cells. If the expected frequencies are not all equal, then we calculate e as n times p for each of the individual category, where p is that probability of that category. Let's put it into practice and try to get some clarity. Here's an example. Fruit soda flavors. A market analyst wished to see whether consumers have any preference among 5 flavors of a new fruit soda. A sample of 100 people provided the following data. Is there enough evidence to reject the claim that there is no preference in selection of fruit soda flavors using the data shown? Let alpha equal 0.05. No preference. What does that mean? If there's no preference for the soda, then that would mean that all 5 of these different flavors are being selected equally. We're looking at a uniform distribution here. So we have a total of 100. That's our n. And then how many different categories do we have? 5 categories. That's going to represent k. 5 different cells, 5 different categories. Here in the table, these 5 numbers are our observed frequencies. This is what the data gave us. So we need to find the expected. For this problem, it's a little bit easy to do by hand, but I will show you when we pull up Google how to do it in Google and essentially in Excel. Even though I'm going to use Google, they are interchangeable in this respect. What we're going to do for this test is the same. So I have observed up top. My expected, since I'm looking at uniform, all of my expecteds, n divided by k. 100 divided by 5, which will give me 20. So I have 20 for all 5 of those groups. Let's write our hypotheses down, and I'm going to write in 2 different ways. The null hypothesis is there is no preference in soda flavor, but this also means the data fits a uniform distribution. So it's fitting a particular distribution. That was exactly our null hypothesis that we talked about before. And our alternative, negating our original statement of no preference, we would say there is a preference. Negating the parenthetical statement, the data are not uniform. The claim is the null hypothesis because it says it right there. The claim there is no preference. And we've got alpha as 0.05. When we run a chi-square test using Google or Excel, the chi-square test is going to give us the p-value back. Since it gives us the p-value back, we need to compare that p-value to our alpha. So we'll do just that. The first thing I'm going to do is I'm going to enter in my observations. So So my observed are in the first row, and in the expected, since I'm looking at uniform, I would take 100 divided by 5, get it to calculate it. In order to use our chi-square test, we have to have the same number of expecteds as we have observed. So the number of observed values and the number of expected values must be equal, or the chi-square test will give you an error. So we have our observes up top, and we have our expecteds down below. And over here on the right, I'm going to type in chi-square dot test, and I need to put in observed values, comma, expected values. And notice that I'm selecting the entire row of observed and the entire row of expected. And then I close the parentheses. The great thing about this test is it already knows what the degrees of freedom are. Even though I didn't say it in working the example, our degrees of freedom are k minus 1. But since Excel knows that I have 5 observed frequencies, it automatically knows that my degrees of freedom are 4. This is categorical data: cherry, strawberry, orange, lime, grape. This is what we mean by using categorical data to now do a test on. We have numbers that represent selections out of a group of 100 people. We're able to do a hypothesis test on categorical data. So here we go. Let's hit enter, and we get a really small number, 0.001234,098, etc. So 0.00123. Need to compare that to my 0.05 as alpha. And I see here that alpha is very much bigger than my p-value. Now let's draw a picture of what this actually means. I have a chi-square distribution. Goodness of fit are always right-tailed. So alpha being 0.05 would be that much area, potentially. But p being 0.00123 would be much less. And so here we would have our critical value and our test statistic. So the p-value, remember, relates to our test statistic, and the alpha relates to our critical value. We still have that connection here in these hypothesis tests that we're doing. Also remember that if we have this picture, in the tails, this critical value to the right would be our rejection region. And notice our test statistic is inside that rejection region, so we would reject the null. And looking up here, this does make sense. We have 32 people selecting cherry, but only 10 selecting grape. That's a pretty big gap. But even though it may seem like a pretty big gap, 22 people, the statistics gives us the evidence that we need to state that, and not just a hunch that we have just by looking at the data. So we would reject the null, and there is enough evidence to reject the claim that there is no preference. There seems to be a preference, and even though here cherry is the most in this one data value, we cannot say definitively that cherry is the preference. Because notice that cherry and strawberry are only 4 away. We could have a completely new sample of 100 people where maybe more in that sample select strawberry over cherry. So we would have to do more research to claim which of these sodas is preferred over the other ones. But we are able to use the chi-square test to determine that we do not have a uniform distribution in this soda preference.